right, on to question number 3 for the practice quiz. So this one's a little weird. You notice right away that it's neither a pendulum nor a spring. This is just a generic question about simple harmonic motion. To help me with this one, I've got a ruler here that is kind of bendy. I don't know how well you're going to be able to see this. It's a little laggy. But it's a ruler where when I apply some force, I can feel resistance back. The important thing here is instead of it being a piece of metal coiled up like a spring or gravity pulling my pendulum back towards equilibrium, the restoring force here, is just the material itself. So the idea is when I apply a force down, this wants to restore or return to its original shape, and it will push up in the opposite direction. So all of our intuition about Hooke's law is actually appropriate to use on this one. Take a moment, make sure you've carefully read the question, and then let's jump in. So the most important thing here is the last sentence. Which of the following explanations is correct about the evidence required to conclude that the mass undergoes simple harmonic motion? A couple things about simple harmonic motion, and then we'll jump into the answer. So for simple harmonic motion, the period and amplitude are constant. And we need a restoring force that is proportional to the displacement. So we're not going to use Hooke's law, but I'm going to put it in magnitude form here. Think Hooke's law. Okay? If you double how hard you press, I just used the magnitude. If you double how hard you press on it, it will stretch twice as far. That's the basic idea. Okay? So let's check in here. Right away we can get rid of the first one. It says the period of oscillation depends on the amplitude. That's never going to be true in case of simple harmonic motion. If you didn't know that, go back and check your notes. That is a basic fact that we need to know. We'll skip over B because you can see right there that's the correct answer. Let's see if C is correct. Mass's acceleration is proportional to the square of the vertical position. Why? Because the elastic potential energy of the mass strip can be modeled by the equation for spring potential energy. Right away, that doesn't strike me as an easy one to eliminate, so let's check D. The motion of the mass repeats after a specific time interval because total mechanical energy is considered to be conserved in simple harmonic motion. So notice I skipped over C. I'll show you why that's wrong in just a moment. The reason that D is wrong is it's missing information about the restoring force. So since it doesn't have that, D is incorrect. There are ways you can have repetitive motion that is not considered simple harmonic motion. For example, if we take a pendulum and let it go too far, like this, it is not considered simple harmonic motion. Remember, pendulum swings need to be pretty small. Now, the details of that are a little bit complicated, but basically, if you let your pendulum go too far, then you don't get this second condition for simple harmonic motion. You don't get that the restoring force is proportional to displacement. So because there's nothing there about the restoring force, we can do an elimination on D. And then taking a second look at letter C, I can show you why we can eliminate it. And then we can talk about on this one how we really could maybe jump straight to B without doing all of these eliminations. The reason that C is incorrect, if we look at the mass's acceleration, it's going to depend on the force. Remember, F equals ma. Now, we know that the type of force that we're looking for, it needs to be like Hooke's law. So let's just say, okay, that it is equal to Hooke's law. And then let's reread it. It says the mass's acceleration is proportional to the square of the vertical position y. So actually, what the heck, let's change it. Instead of kx, let's make it ky. Okay. And there's no square in here, right? It is not squared. So C is incorrect. Now let's actually talk about why B. This one mentions that the F is directly proportional to the vertical position y. That's basically just saying this thing follows its own weird Hooke's law. So in other words, as I displace it, as I apply a force down, that force is proportional to its displacement. Or rather, let me change that to a y. Okay? When we say proportional to, we just mean that K, that spring constant, would be the stiffness in our bendy piece of metal. So there you have it. On this one, you can either eliminate all of them, or you can remember that for something to undergo simple harmonic motion, it needs to have a restoring force that has this proportionality associated with it. That's it for number 3.